Hi everyone, in this video we are discussing quiz 6. So the average was kind of low at a 66%, and not everyone was using the full 30 minutes. So hopefully when going through the answers, make sure you understand why the right answers are right and the wrong answers are wrong to make sure that you don't make the mistakes again in the future. Question 1. What is the preferred conformation for the dehydrobromination of 2-bromobutane by an E2 process? So the main thing that we know is E2 must be antiperiplanar. And then we look at our 2-bromobutane and we know that whether we're taking from either side, we're going to want to identify how many beta hydrogens there are. Because if you have multiple beta hydrogens, then you're going to pick whichever conformation leads to the more stable product, to the trans or the E alkene. So when we look, we see that there are 2 on the right, 3 on the left. That means that no matter what conformation we pick, we got to make sure that it's going to lead to the most stable alkene. All right, so when we look at our options, this first one, we do see that it is 2-bromobutene. So it's, or butane, sorry. So we have 1, 2 is the circle, 3 is the dot, 4 is the front methyl. So the bromine is on 2. And this one ultimately is going to be the correct answer because I see that I have my methyl groups anti, and so that I'm taking this hydrogen, which is leading to the most stable alkene, which will lead me to the trans alkene, where the big groups are as far apart as possible. All right, it'll never work with eclipsed, so we can't do that one. Because we need to be staggered. We need that antiperiplanar, which means that we're staggered. This next one is incorrect because my bromine and my methyl are opposite each other. So that is incorrect because it's not antiperiplanar. The next one, although it is antiperiplanar, that's leading to the cis alkene. So that is also incorrect because that's not going to lead to the more stable alkene. That doesn't lead to the trans or the E alkene. So that is incorrect. So the only correct answer is that first one, where you see that the methyl groups are opposite and you have the hydrogen 180 degrees from the bromine. Question 2. What is the major product of the following reaction? All right, so when we look at this, it might be really confusing at first because the fact that we don't have any other reagents, written other than the strong acid. So strong acid, protonate something. So I'm going to protonate this alcohol. That's my only basic site. So the alcohol is going to take the hydrogen that makes this oxonium ion. Well, if I don't have a nucleophile or electrophile or anything, then I'm going to be doing a stepwise reaction. Like I don't have a strong other reagent to react with this. So my only option is, all right, well, let's have the leaving group leave, make the carbocation. Well, now I see that I have that water. Water is neutral oxygen. That's weak nucleophile, weak base. If it acts as a nucleophile, all that does is make the starting material again. So that's definitely not going to happen. Well, or rather it can, but it'll just keep reacting. But also when I see that I have heat is what is helping me now differentiate the fact that I'm going to ultimately be doing elimination. So you could also think about it as water ultimately became my nucleophile / base, so it was weak. Then I saw secondary, which is where it was coming from originally. So it was the secondary leaving group, again, would be SM1 or E1. And then the heat is ultimately the deciding factor to tell us E1. So then that means that the water is going to act as a base. It takes the beta proton from the more substituted side, because in E1, you always make the most substituted alkene, and it's going to always be trans. So the regiochemistry is that you need to take from the more substituted side that leads to the Zaitsev product. And the stereochemistry is that it'll always be trans or E. So now we're going to consider our products. All right, so out of these, it helps if you draw them into a line diagram to kind of see it right away. This top one would have been if you had an alkyl shift, but if you did an alkyl shift here, that would have left behind a primary carbocation. So we're never going to have that shift to get to a less stable carbocation. So we're definitely not going to have any sort of alkyl shift. The Hoffman product is less stable. You would only do that with E2 and a bulky base, so we're not going to form that one. This is the cis alkene, so it is more substituted, but now my big groups are close together. So I'm not going to make the cis alkene. So transalkene was the only correct answer. Question 3, choose all answers that are true regarding this statement. So we expect the major product of an E2 reaction with a strong hindered base to be the Zaitsev product. No, that is only true if you have a non-bulky base with E2 or for all of our E1 reactions. That's where you would expect the Zaitsev product. Only arise from the antiperiplanar configuration. That's true for all of our E2 reactions. So that is correct. Be the Hoffman product. That is true for the fact that it's a bulky base, the strong hindered base. Yes. Have scrambled stereochemistry at the site of the reaction. That is saying, so scrambled meaning mixed. So that means that you're getting a mixture of your stereochemistry. So that's racemized. So another way of saying that would be scrambled stereochemistry. You can almost think of it as like scrambled eggs are mixed. So it's that all scrambled means is just mixed stereochemistry. That would only be true if it was SN1. Have inverted stereochemistry at the site of the reaction. That would only be true if it was SN2. Question 4. Consider the reaction below. Select all statements that are true for this type of reaction. All right, so we see that we're again doing that same reaction that we did above. So we're seeing a concentrated strong acid. We're going to protonate the alcohol. You're going to get a tertiary leaving group. So the water is weak, that's SN1 or E1. If it did SN1, you would just make your starting material again. But when we compare the tertiary leaving group, SN1 or E1, ultimately heat is the deciding factor to tell you that you're doing E1. Your alkene product will look like that. So ultimately it'll be that product because you would get to your carbocation here, and then you would take the hydrogen from the more substituted side. So that means we're going to look for all statements that are true for an E1 reaction. So that was the difficulty with this one, is that you had to figure out that it was E1 and then find out the statements that matched. So it was also potentially easier because you didn't need to know exactly what the product looked like. You just need to be able to describe what's going on in an E1 reaction. So the reaction is concerted? No, that would only be true if it was SN2 or E2, so that is not correct. The key intermediate controls the stereochemical outcome of the reaction. So I'm really glad that that didn't trip people up, that the key part there is that you get an intermediate. And remember that that intermediate is that carbocation intermediate. You only get intermediates with SN1 and E1. It makes that carbocation. So then you get an intermediate, and that controls the stereochemical outcome because that's what said that you had to have the racemization was because of the carbocation, or you would have the trans or E-alkene because you go through the carbocation with the elimination. So it is that carbocation intermediate that controls the stereochemical outcome. That is true. The reaction results in racemization? No, that would only be true if it were SN1. The reaction proceeds only with inversion? No, that would only be true if it were SN2. Oops. So inversion, SN2. Reaction occurs via antiperiplanar? No, that would only be true if it were E2. The reaction is stepwise? Yes, that's true for our SM1 and E1 reactions. Question 5. Consider the reaction below. Select all statements that are true. All right, so doing the exact same thing. Again, we're looking and we see, all right, I have that tert butoxide is what this is. So that tert butoxide is that base only category telling us that it's E1 or E2. And really, if you see tert butoxide, you see that tert butyl and an O minus, you're probably doing E2. It's a really strong base. So it wants to react right away. But it's also reinforced by the fact that you have a secondary leaving group. So it's definitely going to be E2. Because it's a bulky base, you need to make the Hoffman product. You have to take it from the less substituted side because the large base can only fit on the side that has less carbons or fewer carbons. So the tert butoxide is going to take the hydrogen that is antiperiplanar because it's E2, so it has to be antiperiplanar. And that's going to lead to the less substituted alkene. All right, so we're going to look for all statements that are true for an E2 reaction with a bulky base. So the reaction proceeds only with inversion? No, inversion is SN2. This is definitely not doing SN2. It's a base only. It will never act as a nucleophile. The reaction occurs via antiperiplanar conformation. That is true for every E2 reaction. The rate determining transition state controls the stereochemical outcome. That's true because now you don't have an intermediate. So it's the fact that your orbitals must be aligned properly in order to have that necessary stereochemistry. So that is 100% true. That is the transition state, that orbital alignment, that is saying that is your stereochemistry. So yes, that is true. The reaction is stepwise. No, that would only be true if it were SM1 or E1. Racemization, SM1. The key intermediate is only true for SM1 and E1. The reaction is concerted. Yes, that's true for SN2 and E2. Question 6. All right, we see that cyanide, that CN minus, that is a nucleophile only. So that means I'm doing either SM1 or SN2. The fact that I have a secondary leaving group tells me it could again be SM1 or SN2. Acetone is an aprotic solvent. That's what told me SN2. So SN2 is going to be my major pathway. So the reaction is going to occur where you have your cyanide is going to do the backside attack, attacking that alpha carbon and kicking out the bromine. So we're going to look for all statements that are true for an SN2 reaction. So the rate determining transition state controls reaction. Yes, the transition state, that's SN2 or E2. Yes. The reaction proceeds only with inversion. Yes, that's true for only SN2. The reaction is concerted. Yep, that's for SN2 or E2. Antiperiplanar is only true for E2. Racemization is SN1. Key intermediate means it's one of the stepwise reactions, SM1 or E1. And again, stepwise, SM1 or E1. So these were the 3 correct statements. Question 7. Rank the following alkenes in order of decreasing stability from most stable being 1 and 4 being our least stable. All right, so first thing I would do is draw out what each of these alkenes are. So your 2,3-dimethyl bute-2-ene, bute meaning you have 4 carbons. The alkene is between 2 and 3. You have a methyl on 2 and a methyl on 3. Then your prop-1-ene, so that's 3 alkenes with a double bond between 1 and 2. And in this case, I numbered it right to left. You could have numbered it the other way, it doesn't matter. 2-methyl prop-1-ene. So again, I numbered it right to left. And so I have 3 carbons in my backbone. My alkene is between 1 and 2, and then my methyl is on carbon 2. Then 2-methyl bute-2-ene. I have 1, 2, 3, 4. And for some reason, I did this one going left to right. I don't know why I'm flipping my numbering assignment, but whatever. So I have 4 carbons for the bute. My alkene is between 2 and 3. My methyl is off carbon 2. All right, so when we're figuring out the stability of our alkenes, remember that first we consider a substitution pattern, then we consider sterics. So we're going to say that our tetrasubstituted is going to be the most stable. Monosubstituted is the least stable. So you're going to do it based on substitution pattern, then you would consider sterics. For our sterics, we said that if you are a 1,1 disubstituted, that's less stable than the cis, which is less stable than trans. Or if you're just looking at Z versus E, Z is always going to be less stable than E. You want your big groups as far apart as possible to be more stable. For this, we only actually needed to know the number of substituents. So substituents, remember, are just saying the non-hydrogens attached to your double bond. So for the first one, I have 4 non-hydrogens, so that's tetrasubstituted. For the second one, there is only 1 non-hydrogen. So everything else, there are 3 hydrogens attached to the alkene. So there's 1 non-hydrogen, so that's monosubstituted. The next one is disubstituted. It's a 1,1 disubstituted, but still just disubstituted because the other 2 substituents are hydrogens. And then this bottom one is my trisubstituted because, oops, there's 1 hydrogen, so there are 3 non-hydrogens. So then it's just going to be tetrasubstituted is number 1, trisubstituted is number 2, disubstituted number 3, monosubstituted number 4. So for this, all we need to know was the substitution pattern. Question 8, how many degrees of unsaturation does the following molecule contain? All right, well, we got to remember each unsaturation is represented by a ring and a pi bond. So for this molecule, I see 1 ring and I see 3 pi bonds. So 1 plus 3 is 4. There are 4 unsaturations. If you said 3, watch out for the fact that the alkyne counts for 2 unsaturations because there are 2 pi bonds. Or I guess, and also watch out for the fact that the ring is also a form of unsaturation. So if you chose 3, make sure that you were counting the ring and every individual pi bond. I guess that's true for every option. Make sure you're considering that. Question 9. What is the major organic product of the following reaction? Okay, so for this one, we have our sodium methoxide. That is strong, that's O minus. So that means SN2 or E2. I then see a secondary leaving group, tells me SN2 or E2. And then no temperature is written, so I'm going to assume room temperature, that tells me E2. So I need to pick the E2 pathway. So when I consider this, I need to pick one of the ones that has an alkene. So anything that doesn't have an alkene, immediately I know is incorrect because that's not elimination. When we go to do the elimination, if you look at the Newman projection, looking down the left-hand side, I would see this Newman projection. So what I needed to do was to rotate this front carbon, or I guess you could rotate the back one, but I need this hydrogen to be anti-periplanar to that leaving group. So I had to rotate this in order to get my hydrogen, my bromine anti-periplanar. That's how I see that this is the Z alkene, that I needed my big groups to be on the same side. That's how I get to the correct answer. You can also look at the original if you are not as strong at drawing Newman projections. I see that that hydrogen and the bromine are on the same side. So that tells me I have to rotate this. So I know that I have to rotate it so that the tert-butyl and the isopropyl can't be on opposite sides. They're going to have to be on the same side because I need to get the hydrogen on the opposite side. So I had to do a rotation. So when I consider all my options, the top one was correct because that was the Z alkene for an E2 elimination. So that is correct. The next one, this is incorrect because this would have been the E alkene. That's not possible. This isn't one of the possible products because the E alkene isn't possible from the E2 because it's not antiperiplanar. So E2 cannot make that alkene. Furthermore, if it was E1, you would have seen a carbocation rearrangement. So we're not going to make this product even if we did an E1 reaction. So this is never going to be one of our products. This could be one of our E1 products if you did a hydride shift in order to get the carbocation here. So if you had that, you did a hydride shift so that your H moved over, you get a carbocation here, and then you just deprotonate there. So this is one of the E1 products. You also could have had an alkyl shift and then an E1 product on the other side if you were doing E1, which we're not. Then for the next one, I see that this would be SN1 after having an alkyl shift. So this was the carbocation rearranged. And then now my nucleophile attacked the carbocation, the tertiary carbocation. Then this would be the other SN1 product if I did a hydride shift to get a tertiary carbocation. So both of these would be the major products if I was doing SN1, which I'm not. So they're not the right answer. And this would be the SN2 product where I see the dashed methoxy. But again, we're not doing SN2, so that is the incorrect answer. So there's only one correct answer, and that was to get the Z alkene because the beta hydrogen must be antiperiplanar. Question 10. What is the major organic product? All right, again, we go through the process. I see sodium hydroxide. That's O minus. That is strong. So strong tells me SN2 or E2. I see a secondary leaving group, tells me SN2 or E2. Again, nothing written, tells me room temperature, so that is E2. So I'm looking for my elimination product. I need to have an antiperiplanar hydrogen. The difference for this molecule is that it's a ring. So I cannot do any sort of rotations or anything like that because it's a ring. It's a locked conformation. So what that tells me is if there were no antiperiplanar hydrogens, my only option would be to do substitution. So I need to look for that antiperiplanar hydrogen. So when I look at this, I have a wedge bromine. So I do have I do have 2 possible hydrogens to take from, one on the left, one on the right. But the only one that's antiperiplanar, the only one that's the dash to the wedge, is the one on the right. So that means I have to make the alkene on the right-hand side with the methyl, and the left-hand side remains a dash. That stereochemistry doesn't change because I didn't touch that left side. So when I look at these possible products, the correct answer is this one where the methyl has the double bond. And again, the stereochemistry is lost on this side because it's now sp2 hybridized, but the left side, the ethyl group retains the dash because I didn't do anything with it. The next one is not antiperiplanar, so it's not possible with the E2 reaction, but this could be one of your products if you were doing E1. So if you had to do an E1 reaction, both of these would be your major product, but we weren't doing E1, we were doing E2, so this was my only product. If you had the dashed alcohol, the inversion of stereochemistry, that tells you it would be SN2. The straight line tells me that I racemized the center, so I had loss of stereochemistry. So this would have been SN1 without rearrangement, so that would still be wrong because you must make the most stable carbocation before anything else can happen. So this is like doubly wrong. Then this would be if you had SM1 with a hydride shift to the right, then you would get that product. SN1 with a hydride shift to the left, you would get that product. So if you did SN1, both of these would be your major organic product. But again, we didn't do SN1, we did E2, and so we had to have the antiperiplanar hydrogen, so only the top alkene was our possible product. All right, I hope that makes more sense now. Please let me know if you have any questions. Bye.